Check it out now, y'all.
NanoHub U, online instruction.
Welcome back. In the last lecture, in the introductory lecture, I explained to you that if you could detect biomolecules or at an ultra low concentration, very small biomolecules by these nanobiosensors, then that will enable a wide range of applications like personalized medicine, sort of integrating things with mobile devices like iPhone and so on and so forth. So you must be wondering, what type of biomolecule are we really talking about? So I want to give you a flavor of that, and these would be the actors that we'd be considering. So I will very briefly explain to give you a cartoon picture of how a biosensor works so that you have the big picture within which you can put individual biomolecules. We'll be talking about three types of biomolecules in particular: DNA, protein, and viruses. And then a very important thing in here is how to calculate numbers. Because you see, it's one thing to know how things work, sort of, but it's very different there is to know how to calculate numbers precisely and to get to the conclusions in a quantitative way. And then I will end by talking about diffusion and capture of biomolecules and summarize and conclude. So this is sort of a cartoon view of what a biosensing system might look like. What I have here is the sensor on the bottom, on the red, and the biomolecule T in blue is sort of sitting there. And of course, it will diffuse around. It will diffuse around, and eventually, after a while, it will land on the sensor surface. And once it lands on the sensor surface, depending on the mass or its charge or some other intrinsic physical characteristics, the sensors, if it is sensitive to that characteristics, then it will respond, and then we'll say a molecule has been detected. Now, there are several things about this box. For example, this box is a conceptual box. It could be a beaker. You could be putting a sensor on the bottom of a beaker, or it could be a small droplet of water. For example, a teaspoonful of seawater may contain millions of these target molecules, or it could be a droplet of blood. Or in general, this box could also be a cell within which a protein molecule is moving around and getting latched onto another protein or one of the escape routes, for example, the ion channels that it could go through. So therefore, this is a very generic system that we'll be considering as a framework of our discussion, but I want to get started with the molecule itself, the target molecule T. Now, we'll be thinking about three types of molecules. One molecule would be very small molecules like glucose or nitric acid, nitric oxide. For example, glucose, of course, all of you know, if you have a relative, older relative that is related to diabetes, and then nitric oxide has been sort of correlated to many diseases, but in particular to Parkinson, for example. The second type of molecules we'll be thinking about are DNA and proteins. These are polymers. And third are the invaders, which come from outside, make us sick, virus, bacteria, and even chemicals like DDT, which disrupts cell function and therefore can be very bad for the ecology and for the environment. So three types of molecules. Let me quickly tell you a little bit about each one of those molecules. Now, the thing that we'll be primarily focusing on are the charges associated with this molecule, or the mass or the potential, redox potential, oxidation reduction potential, or even optical index, depending on the sensing scheme we have. We'll not go into the very significant detail in each one of these molecules, only focus on these key characteristics, because for electronic biosensing, these are the things that we detect. Not the entire structure is not really relevant or important in many of the discussions. So just to give you an idea about how things are, how small and big, what small and big mean in these particular structures. For example, glucose molecules will be about a nanometer. The protein molecules that we'll be talking about in the order of 10-20 nanometers. Viruses and bacteria are somewhat larger. A virus could be 100 nanometer, and a bacteria about a micron or so, couple of microns or so. Of course, there are other molecules which are much bigger. We'll not be considering that. Smaller molecules also is not something that we'll discuss. So let's discuss a little bit more about these molecules, biomolecules. The first one is glucose. As you know, the formula is pretty simple. Many of you may remember from your high school or college courses that it is C6H12 and O6, and essentially there is a carbon backbone. All the white atoms are hydrogen. Relatively lightweight molecule. It's 180 kilograms per mole. So a Avogadro number, 6 times 10 to the power 23 number of molecules contains about 180 gram of glucose. And the size, as I mentioned before, is a 1 nanometer. The important point here for this molecule is that they are too small to be detected by a mass-based sensor. Let's say cantilever-based sensor. It's very small. And the second is it doesn't carry much charge. This is all generally charge neutral. And so potentiometric sensors may not also work. The things that works the best is amperometric sensors. And in fact, since 1960s, most amperometric glucose sensors have been based on being able to measure the electron affinity through amperometric sensors. Now, the second class of molecule, which is a little bit bigger, but also very, very important, are these DNA and protein. So DNA, as you can see, this is deoxyribonucleic acid. This is essentially a polymer chain. Each one of these elements, there are 4 types of these elements. So there can be this diamonds. There are 4 types of diamonds, A, T, C, G for short. And essentially when you string them together, you have a DNA molecule. Now the size of the molecule that we'll be interested in is on the order of maybe 100 to 1,000 unit. Not very long. So in fact, human DNA is 4 billion base pair long, but we'll be chalking it off and only looking at segments which is 100 to 1,000. So relatively small molecule in that sense. Now, each one of the diamonds, if you looked inside, a little bit, then you will see that there is a 5-ring carbon sugar, and the base is this ATCG, are this nitrogen molecule, nitrogen atom containing base. And there is also a residue of phosphoric acid. What do I mean by that is that this was really H3PO4. The hydrogen went away, making it charged or positively, negatively charged, because the electrons were left behind. And generally, these molecules don't line up next to each other in a linear fashion, but they are staggered. The sugar connects with the phosphoric acid residue of the next molecule, giving rise to this helical structure, because this is shifted. So therefore, it keeps sort of going around. Bottom line, each one of them carries a charge on the order of 1 to 2 electronic charges. So if you had, let's say, 300 base pair long DNA, then the charges will be 300Q to 600Q, somewhere in between, depending on the pH condition that we'll discuss a little bit later. The mass is also significant, almost 300 Dalton. Dalton is a unit of proton mass, sort of atomic unit. And so therefore, if you had, let's say, 100 of these elements, that will be 3,000 Dalton. That's pretty massive. So you can actually measure it in mass-based sensors, but also you can measure this in a charge-based potentiometric sensors. Next up is protein. Protein is again a long chain, almost very similar to DNA. In fact, every 3 bases of the DNA creates one protein. And since there are 4 bases to choose from, so there might have been 64 combination of proteins. Instead, there are actually 20. So you can think about it as if you have a necklace that has 20 different colored beads, and these are strung together. Once again, very similar structure. Each one of the diamonds is essentially a simple molecule with a carbon in the bottom, in the center, and there is this residue. And depending on this molecule, this is a complex molecule shown here in the box, there are 20 different versions of R. And in the solution, when you put the protein in the solution, let's say in the physiological environment, then some of these R's are positive, some of them are negative, some of them are neutral. Unlike DNA, you see DNA are all negative. Here, depending on the surrounding conditions, there can be positive or negative. And so, depending on the protein that we have, for example, this is PSA, prostate-specific antigen protein. In that case, it will have some combination of these 20 residues, and so therefore this can be positive or negative or may have 0 charge depending on the environment, aqueous environment around. So one should certainly be able to detect it by potentiometric systems, potentiometric sensors, but also the mass is significant when you have a long string. Let's say this one has 261 amino acid. Each one of them is an amino acid, 261 of them multiplied by 125 Dalton. That is the mass. And so you should be able to detect it at relatively low concentration using mass-based sensors as well. Now, there are many markers of interest. There are many biomedical instrumentation. For example, the molecule that I just showed was PSA. This is a marker for prostate cancer. Anytime a person has a heart attack, the first thing the doctors do when they arrive at the hospital is look for this particular protein, cardiac troponin T, in order to see how significant the heart attack was. There are other types of proteins associated with ionizing exposure, and this BRCA1 and BRCA2, this stands for breast cancer 1, and although breast cancer 2 is really a marker for the ovarian cancer. Bottom line is identifying these proteins in a solution at very low concentration is extremely important, and therefore there are many tests associated with each one of those protein molecules, and you will see some of them during the course. Next up, virus. This looks very bad, looks like a dangerous pathogen, which is what it perhaps is. Now, this virus is in one hierarchy up of the size of a modern transistor. Let's say if you had an iPhone with a 20 nanometer or 30 nanometer technology, then this virus, size of the virus will fit nicely on top of one of those transistors in your iPhone. This outer coating is a protein that we just discussed, long chains of this, and inside there is this DNA. Now this combined structure is on the order of, let's say, 100 nanometer. But this generally doesn't carry significant amount of charge or stable amount of charge, so therefore very difficult to use potentiometric sensors. But look at this. This is massive. And so therefore even a few viruses, let's say 10 to 100 or so, you may be able to detect it with cantilever-based sensing. And so therefore, this is certainly an option to detect this type of quantities, this type of biomolecules. Of course, you always have the option of breaking this apart and looking at the DNA or RNA directly. That gives you one option of identifying the viruses. The other thing you can do is that although this is charge neutral, you can have a potentiometric sensor which has a certain amount of pre-existing charge and allow the viruses to come and displace some of the charges. And so therefore, whatever was the sensor's characteristics in the beginning, based on the pre-existing charge, will certainly be changed now, because some of them have been replaced by this charge neutral quantity. And thereby, although this is charge neutral, one may be able to detect it by potentiometric method. But of course, there are other simpler methods to detect it. Next up, a little bit bigger, the size of a 1970s transistor, is the bacteria. So if you open up an old computer, maybe you'll find something of this size, about 3 micron here, much more complex structure. Don't worry, we don't have to know any of these structures. The bottom line is that this is a relatively heavy molecule which can be captured on a sensor surface, and the mass and the size will essentially allow us to separate it from other parasitic molecules. Now, one interesting fact is that about a millimeter cube of soil, let's say, can have tens of millions of bacteria. In fact, 1 pound, every pound of our body weight is made of bacteria itself. So it plays a significant role in the physiology or well-being of human beings. So it's a very important biomolecule that we should be thinking about. Very quick examples now. I told you about this 3 types of small, medium, and large biomolecules. Now, let me give you an example about the density of small molecules, because you should be comfortable with numbers. Let's say you just have taken a 1000 milligram headache medicine. How much would your concentration of this molecule would be in your blood? Easy calculation. You can see this formula is almost like the glucose formula. It's a little bit lighter. It has 151 151 gram of this Tylenol. You can just add up the atomic weights of this, and 151 grams of it will contain the Avogadro's number of molecules. So 1000 milligram is like a gram. So that gives you, that will contain 4 times 10 to the power 21 molecules of Tylenol. And our blood is about 5 liters. And if you then convert it to per liter, then 8 times 10 to the 20. And as a fraction of the Avogadro's number, that gives you 1.32 millimolar. And if you remember my blood test result from the last lecture, then you might remember that this concentration is very high. In fact, equal to some of the concentration of other molecules that we have in our system. So the headache medicine will work in minutes, as it often does, especially at this very high concentration. That's about small molecules. What about larger molecules? But before we get there, the important thing is about sample volume. It's very important to think about how big a volume do you need in order to be sure that you have the target molecule. Because no matter how sensitive your sensor is, if you don't have any molecule in your sample volume, then of course you are not going to detect anything. So for example, let's say a cancerous organ is releasing at a very early stage of disease about 10,000 cells, and we want to know whether if we just went to the doctor drew a centimeter cube of blood, or did a finger prick and then drew a millimeter cube of blood, whether there is any chance that the doctor will be able to find the cancer cells. Let's say, can it be done? No matter how sensitive the sensor is, let's give the doctor the best technology he might possibly have. And the answer is that answer might surprise you. You see, first of all, 1 centimeter cube of blood will contain 2 cells, and a millimeter cube of blood will contain almost nothing. And so therefore, statistically it's almost impossible that from a millimeter cube of blood that you are going to pick up this disease? Not possible, because the chances of getting a cancer molecule in there is very small. But even if you took a blood, about a centimeter cube of blood, then you see, then the Poisson statistic says that on average, if there is 2, there is also probability that you may have 3, or you may have 1, or you may have nothing. So in fact, there is a 13% of the time you can show that you will essentially, the sample will have no molecule, no cancerous cell at all. The doctor will say that you are good, you can go home, which is a false negative. And in fact, whereas there was a problem, and if you could detect it early on, that would have helped. So sample volume is very important regardless of your sensitivity of your sensor, because first there should be molecule before you take the picture of it or by the sensor. Now, let me tell a little bit about, and there where I will conclude, is about the molecules diffusing around, because the biomolecules, when you put in a solution, they don't stay put. Rather, they drift around, diffuse around, and eventually are caught by the sensor. Now, the diffusion process is known as a random walk. If you look at the biomolecule, it could be a protein or it could be a DNA, you will see that if I had a microscope, and if I could somehow look at that molecule, the molecule would zigzag around in the solution. And every molecule that you put will take a different path. Why do they zigzag around like that? Because there are invisible water molecules around that, and this red molecule essentially is bumping off against these speed bumps in a random direction, and that gives it, reorienting it every time, so that gives it this Brownian motion. Now, this Brownian motion is very important, because this tells us that although we cannot say exactly how far a molecule will go, a given molecule, let's say given molecule number 1, how far will it go at the end of time t, but we can say on average, if you injected at the same point 1,000 of these red molecules, each one of them will go a slightly different distance, but there is an average distance that it will go. And that is the statistical average, is a very important number, diffusion distance that we'll have to think about. But first of all, the statistical distribution of this diffusion is described by this diffusion equation. Here, rho is the probability of finding this red molecule at a distance r at a time t, and the d is the diffusion coefficient. If it gets scattered more by these molecules because it's more viscous, d will be more. If the red molecule is bigger, let's say a protein compared to a glucose molecule, the d will be smaller. And so the diffusion equation tells us that how this molecule on average will drift around. Now, if you have forgotten the diffusion equation, I will have an appendix later on in which I will derive it. For the time being, I hope you can accept the equation as is, and we can move on. So let me tell you how far will it move. So the diffusion equation, the way I have set up, this is the original diffusion equation, and I am assuming just like a drop of ink in water at a given point A, I have put it in this one-dimensional space as a delta function, and which is the density at time t equals 0 when you started, everything was concentrated at one point. Then, if you come a little bit later, where will the particles be? Of course, they will not be here anymore. They'll be walking around, and after a time t, essentially they will diffuse around. They will diffuse symmetrically on both directions, and this is the solution. N divided by 4 pi dt, e to the power x square over 4 dt. This one is in one dimension. If you had in 2 or 3, this square root will be replaced by the corresponding power. And if you looked at the average displacement of how far it has gone, you will see on average the square of the displacement is 2 dt. And as a result, the molecules essentially diffuse approximately square root of dt from the center after a time t. Depends on the diffusion coefficient, of course, but in general, that average number is what we are looking for. So that sort of concludes my basic introduction to biomolecules. So I mentioned to you that, of course, we want to detect a range of biomolecules to enable nanotechnology, nanobiotechnology. And these biomolecules include from glucose all the way to bacteria for various diseases. Now, as I mentioned, the typical sensors detect millimolar. That was in my blood test, that was in the headache medicine, and so therefore this is a relatively large number. The promise is that even when the concentration is orders of magnitude smaller, these nanobiosensors, the one that we have not discussed yet, we'll begin to discuss in the next class, that can detect femtomolar concentration, can detect at a very early stage of the disease progression. Of course, the sample volume must be large enough so that it has the statistically meaningful number of molecules. And then I started talking about how the molecules walk around. And the bottom line was it follows, on average, the diffusion equation. And the diffusion, it goes about a distance of square root of dt on average within a time t. If the molecule is big, d is small. If the molecule is viscous, d is small. So for each molecule, there is a diffusion coefficient, and therefore it allows you to calculate how far the molecule will go once you have put it someplace at time t equals 0. That's it. So in the next class, I will talk about the next piece, which is the sensors themselves, because now the biomolecules are moving, they can come and get captured by the sensor surface. So we'll talk about the sensors next time. Take care. Thanks.